So let's take a look at this work and energy problem. And this is a good problem because it illustrates a lot of the process on how we go about breaking down a work and energy problem. So we have this 2 kilogram block that's acted upon a spring with the force constant of K being influenced by friction. So here we have friction along with the spring scenario. The static frictional force and the kinetic frictional force are both 50 newtons. I think what they mean is the maximum static frictional force is. I don't know if you know if it were static friction, like you don't know the exact amount, it wouldn't necessarily bounce. So I'm going to say like the maximum static friction is 50 in the kinetic friction force. The object is released from rest at x equals 5 meters, so where it is stretched by 5 meters. So what they're saying here is you have this block here, oops, and let's say there's a relaxed length of the spring, but it's being stretched at this point, right? So the block is like this. This is where it's currently at, x equals 5. And then like x equals 0 is the relaxed, let's call this the relaxed length of the spring here. So this is the natural length of the spring, L0 maybe. But basically it's being stretched by 5 meters. First part is, will the particle move when it's first released? And how do you know? So because of, the reason it might not move, right, is because the friction, the static friction might be too great, or like we can't overcome the maximum static friction in order to get it start moving. So in order to understand that part, we got to draw a free body diagram, right? So for this step, we're going to draw a free body diagram, and then we're going to do F net equals ma. Really, at this point in the year, there's only 3 techniques that you have. You either have kinematics, you have forces where you draw a free body diagram, or you're going to use work and energy. You know, there's some other techniques later, momentum and rotation, but really it's between one of those 3 techniques. So we're going to draw a free body diagram here. I have mg. I always have gravity, and then I have a normal force from the ground, and then I have a spring exerting a force this way, and then friction is going to be opposing that, and maybe holding it in place if it's static friction, or if it's kinetic friction, it's going to, go against this rubbing motion against the surface here. Nothing else is touching it. Oops, that's not FSP, that's force of friction. Nothing else is touching it, so there's no other forces that are acting on it, right? So that's our free body diagram. 2, do F net equals ma. Well, actually, we got to sign positive and negative directions. Now, in this case, because we said, we already said our orientation, so we said right was positive based on this coordinate system here, right? So when we do F net equals ma, we've already established, well, actually, sorry, step 2 is assign directions and identify acceleration. Now, in this case, we don't know if there's acceleration. Acceleration could either be 0, or if anything, it's going to the left, right? One of those two. So now we're going to do F net equals ma. So horizontally, in the x direction, you have force of friction to the right, which is positive. Spring force to the left, which is negative, equals ma, which might be 0. We don't know that it's 0. So let's look at the force of friction. Well, we want to compare the spring force to the maximum static frictional force. So what is the spring force going to equal? It's going to equal kx, which in this case is 100 times 5, which is 500 newtons. And then the frictional force, the maximum static frictional force, we say is 50 newtons. So we're definitely going to overcome it, and it's definitely going to accelerate. So, right, so 500 is greater than 50, so it will slide left. Or you can think of it from this equation. It's going to have a negative acceleration because the friction will be 50 minus 500 will equal 2 times a. You can find the initial acceleration. It's going to be a negative number, right? And so what does a negative mean is because we said right was positive, it is going to accelerate to the left. Okay, so that's part 62. Let's look at 63. What is the speed of the object when it reaches x equals 0 for the first time? Now, we cannot use kinematics. So one way we solve for the speed of something is we use kinematics. Why can't we use the kinematic equations here? Is because the acceleration is not constant. As the block moves, the spring force, this is going to change right here. If any part of the forces change, the acceleration changes. Thus, the acceleration is not constant. So our kinematic equations only apply when the acceleration is constant, right? So I can't use kinematics. No, it will mess you up. It'll give you the wrong answer. So the only other technique we have is work and energy. Work and energy. And the key equation is work is the change in energy. Now, the first step in a work and energy problem is to identify the system. What is the system going to be? Generally, it's always going to be the object that's moving. So in this case, it's the block. But because we have a spring, we're going to include the spring in the system. Okay, so block and spring. There's no change in height, so I don't include the earth in the system. You could, but there's no change in height, so there's no reason to include the earth in the system. All right, second step is to draw a free body diagram. Okay, so when we do a free body diagram here, we already did it here. And now we want to identify what forces are doing work. So if we look at our free body diagram, and during the motion, what's going to do work? Well, the displacement is to the left, right? That's the direction of the motion. So the normal force and gravity don't do work because they are perpendicular to the displacement, right? There has to be a component parallel to the displacement to do work. The spring force also doesn't do work because it's internal to the system. We've captured it as part of the system. So we're going to capture it as part of the energy, not part of the work being done. So the spring force also doesn't do work. So the only work being done is by friction. Now friction is a constant force, so it's negative, and it's a negative work because the displacement and the frictional force are opposite directions. That's a rule. If the force and the displacement are opposite directions, the work is negative. So it's negative force of friction times the displacement. That's negative 50. And the displacement, it went to 0, so it travels 5, right? And that's negative 250. So ultimately, it has to be a negative number at the end, okay? Negative 250 joules, because the force and the displacement vector are opposite directions. 4, calculate the initial energy. So this is the start of the motion, the initial energy. Now it was released from rest, so we know the velocity is 0. So energy, because we've included the block and the spring, there's two forms we always have to consider. The kinetic energy and the spring potential energy. This is only because that's how the system is designed. If you consider the block, you always consider the kinetic energy of it for any objects that are moving. And then if you include the spring, you're going to include the spring potential energy. Now, the initial speed is 0, so it has no initial kinetic energy. How much spring potential kinetic energy it has? It has 1/2 k, and it's being stretched a distance 5. And that's going to be, what, 1250 joules. 5, we want to find an expression for the final energy, the energy at this point. Again, our system dictates that we're only considering kinetic energy and spring potential energy. So at this point, all right, does it have kinetic energy? Sure. Does it have any spring potential energy? Well, we're now at the relaxed length of the spring. Okay, so there's no spring potential energy at this point. So then we're just left with 1/2 times 2 times v squared, which is just v squared. And now the last step is we're going to do work is the change in energy. Final minus the initial. And that's going to be negative 250 is the final energy, which is v squared, minus the initial energy, 1250. You find that v squared is 1,000 by adding the 1250, and so v is the square root of that. And that gives you 31.6 meters per second. Okay, and that matches the answer key there. All right, 64. What's the maximum negative x position reached by the object? Okay, so now what we're going to say is it's going to keep going, because it has some speed here. It's going to compress, and it's going to come to some point here. Okay, and we'll call this x. All right, and I want to know what that is. We use a different letter. We use d, just to not confuse it with the coordinate system. So we'll call this d. D is the distance. I would like to know what that is. All right, so we're still going to do work as change in energy, right? Might as well do it from here to here, maybe. Okay, like that point to this point. So same system, same free body diagram, except from here to here, the friction acts the opposite direction. So the friction is going to... no, actually, sorry, it's moving from there. Friction is the same direction. So everything is basically the same. Steps 1 and 2 are identical for the work and change in energy. Let's look at the work calculation. It's negative force of friction times the displacement, which is negative 50. But how far does it move from here to here is d. So negative 50d is the work expression. How about the initial energy? The energy at this point. So now this is the initial because we're going from there to there. The initial energy is just, we had an expression for it. It was v squared, which is 31.6 squared, which is 1,000. Okay? Final energy. At this point here, the velocity is 0 because at maximum compression, the speed is going to be 0 because then it's going to turn around and go the other direction maybe. Or at the minimum, you have to say, if there were any speed left, it would keep going. It would go further and compress even more. So right at the maximum compression, its velocity is 0. So again, we consider the kinetic energy and the spring potential energy. But there's no kinetic energy because the speed is 0. So this is 1/2, 100. And how much is... Now the spring's been compressed by distance d. So d squared. Which is 50d squared. Okay? And so then finally, we're going to use work is the change in energy. Right? So that's negative 50d equals 1,000. Sorry, final minus initial. Final minus initial. I was like, right now, what's the final? What's the initial? Final minus the initial. And then we're going to move this over. 0 is equal to... Now, this is quadratic in d. See this? So we got to set it equal to 0. And it's just a math problem at this point. We're going to divide by 50. D squared plus D minus, what is that, 20? No, 40. 20. And turns out this one factors into D plus 5, D minus 4. So D has to equal negative 5 or D equals 4. Now, when I used this D calculation, I actually assumed D was a positive number. Why did I assume it was positive? Because this was going to be a negative work here. So, a little bit tricky to see, but the D is actually 4 meters to the left. Okay? And so that's why the X is equal to negative 4 meters. That's the negative X position. It's 4 meters to the left of where it started there. Okay? So I hope that clarifies. That's the process for work and energy. That's how we're always going to break down a work and energy problem.